In this video, we'll discuss graph traversals and backtracking.
Graph traversal, or graph search, refers to the process of visiting each vertex, or node, in a graph. There are two commonly used graph traversal methods, depth-first search and breadth-first search. We will first discuss depth-first search, or DFS, which explores as far as possible along each branch before backtracking. We will elaborate on the concept of backtracking later in this video. A stack is often used to keep track of nodes visited. This is a DFS algorithm, which does the search recursively, without using a stack. To conduct a depth-first search of a graph, G, we first mark all vertices in G as not visited. Then we start with any vertex U in G and mark this vertex as visited. Next, if there is a vertex V that is adjacent to U that has not been visited, we choose this vertex V as a new starting point and call the DFS function recursively. That means we start with a vertex and go as far deep as possible. Then we go back to this vertex and visit another adjacent vertex of it. We continue thus until all vertices are visited. Like this figure, we can start with vertex 1, then visit its adjacent vertex 2, then 3 which is adjacent to 2, then 6, which is adjacent to 3, then 5, which is adjacent to 6. We cannot go further, so we backtrack to 1, then we visit the other neighbor of it, vertex 4. Then 7, which is adjacent to 4, then 8, which is adjacent to 7. Of course, alternatively, we could first visit 8 and then 7. A depth-first traversal of a connected graph generates a spanning tree. A tree is a special graph that does not have any cycle. The spanning tree consists of all the vertices of the graph and the branches traversed. This figure shows the spanning tree associated with the DFS of the above graph. The dotted lines are the branches of the graph that have not been visited in the DFS. If the graph considered is not connected, a DFS generates not merely a single tree, but rather a forest of trees, one for each component of the graph. The time complexity of DFS is theta, maximum of the number of vertices and the number of edges in the graph. We may also use a stack, which is last in first out, or LIFO, to implement the DFS search as shown here. We start with an empty stack and a vertex U. We push the vertex U onto the stack. While the stack is not empty, we pop the vertex at the top of the stack. If the vertex has been visited, we continue to pop the stack. If it has not been visited, we mark it as visited and push all its non-visited vertices onto the stack. A newly pushed vertex is always at the top of the stack. The last in first out property of a stack makes the search go as far deep as possible. When it could not go further, it backtracks to the previous vertex it has come from. When the stack becomes empty, all vertices have been visited. DFS can be used to traverse a directed graph also. For example, in this figure, we can start with vertex 1, then visit 2, then 3 and we cannot go further, so we start from another adjacent vertex of 1, so we visit 4, then 8, then 7. We cannot go further and there's no more unvisited adjacent vertex of 1. So we start from another unvisited vertex, 5 then visit its unvisited neighbor 6. We obtain two spanning trees as shown in this figure. Again, the dotted lines show the branches that were not traversed. Now let us examine another graph traversal technique, breadth-first search. In a depth-first search, when we arrive at some vertex U, we next visit a neighbor of U, then a neighbor of this neighbor, and so on. In contrast, in a breadth-first search, when we arrive at some vertex U, we first visit all its neighbors. Only when this has been done, do we visit vertices further away. A queue is often used to implement a breadth-first search. A queue is first in first out, or FIFO. It has two operations, NQ, meaning enter the queue, and DQ meaning delete the front element from the queue. Here is the breadth-first search algorithm. We start with an empty queue and some vertex U, which is pushed into the queue. While the queue is not empty, we delete the front vertex from it. If the vertex is not visited, we mark it as visited and then push all its unvisited neighbors into the queue. Because of the first in first out property, we always visit its neighbors before proceeding further. In this example, we start with visiting vertex 1, then visit its neighbors, 2, 3, 4, then the unvisited neighbors of 2, 5, 6. Now 3 has no unvisited neighbors.
So we visit the neighbors of 4. There's 7 and 8. Okay. So there's the very first search. Okay. And again, we obtained a search tree, a spanning tree, okay, like this. Okay. Both DFS and BFS has time complexity theta, maximum of number of vertices and number of edges in the graph. Okay, so we take the maximum of these two values. Now, BFS is often used to partially explore an infinite or very large graph. This is an example to elaborate this concept. Okay, we can obtain a number by two operations starting from 1. Okay, we can multiply the numbers by 2, and that operation is division by 3. We dropped the fraction part. Okay, so we start with 1. So the 2 can be obtained by 1 times 2. And for example, 10 can be obtained by 1 times 2 times 2 times 2 times 2. That's 16 divided by 3, we get 5 by truncating the fractional part. And then multiply that by 2, we get 10. Okay? So this is the tree of the numbers that's obtained. So 1, we get 2 by multiplying by 1 by 2, and then 2 times 2, we get 4. Okay? 2 times 4, we get 8. Okay? And of course, if we divide 8 by 3, we get 2. Okay, so there could be a branch from 8 to 2 also, but we omit all the backward links here for clarity. Okay. And 8 times 2, we get 16. 16 divided by 3, we get 5. Okay. And 16 times 2, we get 32. And 5 times 2, we get 10. And so on. Okay. Now, if we want to search for a certain number in this tree, say we want to search 13. Okay. If we use depth first search, we may miss 13 because in depth first search, we go as far deep as possible. We may go along this path, okay, and go to infinity. So we may never get to the lower half, okay, lower bench, okay, 13. So we'll miss all these numbers when we do the search. On the other hand, if we use breadth first search or BFS, then we'll be sure to find the solution for that number, like 13, because we find all the labels before we proceed further. Okay? So we always can find the number. So that's the graph traversals. Okay, and we mentioned earlier about backtracking. So here we discuss in more detail about this backtracking technique. Okay, so we have used that in the depth first search. Okay. Now, we can use backtracking to solve a problem by trial and error, but we do that in a well-organized manner. Okay? And in this method, we never try the same thing twice. Okay? If the problem is finite, we will eventually try all possibilities. Okay? If the steps tried do not need a solution, some or all of them may have to be retraced, and the relevant details discarded. Okay? Just like the depth first search. Say we go to start 1, we go all the way to 5, and then we cannot go further. So we go back to 1 and start another route. Okay. If we want to find 8, okay, first we go try all this, and then later we try this, we get to here. Now, we discuss another example, which is well known, to elaborate the backtracking technique. This is called the 8-queen problem. This problem is to put 8 queens on an 8x8 chessboard so that no 2 queens will attack each other. Okay. We want all the queens to be non-attacking. Okay. So a queen will attack the other if they are on the same row, same column, or same diagonal. Okay. So, for example, this is a solution. So no 2 queens here will attack one another. Of course, we can solve this problem using brute force. We try a configuration and check whether it is a solution. Okay. If we do that, then there could be a lot of trials. We have, say, 8 queens to place, and totally there are 64 squares because we have 8 times 8. That's 64. So 64 choosing 8. So the combinations would be more than 4 billions. Okay. It is equal to this. Now, if we put some restrictions on it, only 1 queen in each row is allowed. Okay? Then each row can have 8 choices. So this row has 8 choices. This row has 8 choices. So today that means we have 8 to the 8 choices. Okay? So there's about more than 16 million. Okay? If we further restrict the placement, we reject position whose column or diagonals are guarded. Okay, so that means so in the first row you can have 8 choices. Okay, and the second you only have 7. Okay, because you cannot put a queen in the same diagonal. And then the third, you have 5 and 4 and 3, 2, 1. So the number of choices would be 8 factorials, about 40k. Now, if you use backtracking, then it will be more efficient. So backtracking is an efficient approach. Using this technique to solve the problem, when we place a queen on a square, we check if it is under attack. If no, proceed. If yes, then we will move the queen and backtrack. Okay? And try the next position. Okay? And and when we place the queen, we have to place only 1 queen per row, satisfying the conditions. Okay? So that means the placed queen is not under attack. Okay? And we place only one queen per column, satisfying the conditions. Okay, so we can start from, say, column 0. Okay, and we place a queen in a position here in one of the rows, and then move to the next column and the next column. Okay, and at a certain time, when we place a queen, okay, at a certain row and column, okay, this column we try this row, okay, the black square, okay, then we have to check whether it is under attack. That means we need to ensure that the row is clear, so the green squares, and the upper diagonal, the red squares, is clear. The lower diagonal, okay, the blue squares, okay, is cleared. Okay. Cleared means no queen is in the position in any of the square. Okay, in this row, in this diagonal, or this diagonal. Okay. Now, suppose the variable row points to the current row. Okay, then to check whether the row is clear, it should be pretty straightforward. We use an index, maybe C, to point to the column we consider. Okay, so we consider this row, this column. If it is clear, then we decrement C, consider this column, okay, same row, and then consider this column. And we need to consider the upper diagonal. We use another index, row index R1, okay, points to a row higher than the current row, R1, okay, and we just need to check whether the square specified by the R1C is cleared. Okay. If yes, then we try the other one by decrement R1. That means you move one row up, okay, and decrement C. Okay, we try to test this square. For the lower diagonal, we do the same thing. So we use another row index, okay, R2, okay, and we check whether the square, which is specified by R2C, if it is cleared. Okay. If it is cleared, then we test the other one. By increment now, increment R2 and decrement C. Okay. So by checking this and this, we will know whether the queen we placed is under attack or not. Okay. Now this is the complete implementation of this problem. And so we can create a class called Queen 8. Okay. So with a constructor, okay, we create a board, means all squares are empty. Display the board is to show the where the queens are at. So we use an X to show that it is empty. If it is not empty, we use a Q to represent it. So this is the display board. Okay. If it is a queen, then we output Q. If it is, otherwise it is empty, as X. Okay. And we define the elem square, which is queen or empty. Okay, and the board is the square 8 times 8, 2D. Okay, and then to set the queen means to set this square at row and column to be queen. Okay, it's the set queen. set queen is this. Okay, we just assign queen to this. And we move queen. That means we set this row and column, that square, to empty. So these are pretty straightforward, to empty. And now, is under attack is the implementation of what we just discussed. We want to check whether when we place a queen at row and call, will cause any attack by other queens. Okay, so that's the implementation of what we discussed. So we start from column -1. Okay, so means if this is column col points to here, we start from c equals column -1. Okay, one column less. Okay, and this is row. So if there's a queen, okay, in that row column, okay, then that means it is under attack. Okay, so this is for checking the row, and then we check the upper coordinates. Okay, if this is not true, okay, sorry, we check the upper diagonal R1C. Okay, if there's a queen, then we return true. Otherwise, we decrement R1. Okay, move to the next row. I mean the row higher. Okay. And again, we do therefore out to the lower diagonal. If there's a queen, then we return true. Otherwise, we increment it. Okay, when we go down, we increment out to 3, 4. Okay. So if it is not under attack, okay, then it returns false. If everything is cleared, okay, we do not find any queen in any of these positions, then we return false. Okay. So this function tells us whether when we place a queen at these positions, okay, it is under attack. Okay. And now, this is the function place queen. Okay, that's where the backtracking comes into place. Okay, place queen will start with 0. So we call this function. Okay, we start with 0, and done, of course, false. Okay, it's not done. Okay. So we start from column 0, and then if we do this recursively, increment the column 1 at a time. Okay. And if it's larger than 7, that means it's done. Okay, that means it's true. Okay, we're done. Okay. Otherwise, we continue to consider the next column. And we do that recursively. Okay. Now, for each column, okay, we start from row equals 0. That means this one. Okay. We start from a certain row equals 0. We place a queen there. And we have to check, okay, whether by placing a queen there, okay, and at this column, okay, whether it is under attack. If it is under attack, then we try the next row. Okay. Now, if it is not under attack, okay, then we can continue. That means we consider next column. Okay, so we can put the queen there. Okay, set queen at that row column. Okay, because by placing it there, it is not under attack, so we can put it there. Okay. And now we have to call this function place queen column +1 and done. Call +1, that means next column. Okay, and this, okay, will tell us whether by putting row column here, and subsequent action could be successful. Okay. If it is not successful, that means it is not done. Okay. Then we have to remove the queen. Okay. So that's backtrack. Remove the queen at this row and column and try next row. Okay. So basically, you can think in this way. So suppose you are the function place queen at the row column. So you call this function place queen. You can regard it as a black box. So this will tell you whether your action of place the queen at row column is successful. Okay, it's for it to be successful to continue. Okay, if not, then you have to remove it. Okay, and try another row. Okay, if you exhaust all row, okay, it failed, then you tell your caller. Okay, so the caller will rely on you. Okay, and you rely on this, and so on, to do it. So there's a recursive process. Okay, and so this is a problem solved using backtracking technique. Okay, we can compile this, copy and paste and compile this. Let's copy this. Copy it. Okay, and we call this queen a.cpp. Okay, so we are copy this program, the complete program that we just discussed. Okay, and we can compile it. Okay, and then we run it. Okay, so you can see that if found a solution, so these q's are the queens. Okay, x are the empty squares. Okay, and you can see that the queens do not threaten each other. Okay, so this is one of the solutions. Okay. So you can try this yourself, okay, and think over it. Okay. Okay. That's what we want to discuss today. Okay. Thank you for watching.